recap for the sake of the notes, looking for where the function is increasing. I asked you then where is it decreasing. What I'm trying to make a point of now is that when we talk about intervals, we're talking about input values. So we need to identify the input values where the interval is positive and where the outputs are decreasing in value. So again, we have two of them. We have this arm and we have this arm. Now, what's this got to do with what we're talking about in calculus? The whole semester so far, we've really talked about one topic. What is that? Derivatives. Okay? So now the question could be, a big so what? How does this discussion of increasing and decreasing portions of the function connect with our discussion of derivatives? What would you say about all of the tangent lines? If we were to take a tangent line, well, let's see, we could actually do that, I guess. Let's take a tangent line here. I'm going to attach it someplace right about there. And then what I'm interested in is the, with derivatives, we take tangent lines and we're interested in their slopes. So let's take a slope of that tangent line. We'll put it right there. And we'll make that tangent line just a little more prominent. If I take this tangent line, the point of tangency, if I can, come on. There we go. So we don't lose track of what this means. Okay. If I take that tangent line, that point of tangency, and I move it anywhere along this portion, what's the same about that tangent line slope? It's negative. It will remain negative until I get to where? The what? Until I get down here to -1. And then somewhere in here, it's a little hard, that's supposed to be 0. If you look at that, it's a negative, it's in scientific notation. And then I move that point along here, what's happening to the derivative? Positive. The slope of the tangent line is positive until I reach this turning point, whatever that turning point is, and then I get 0 again. And then the derivative, the slope of that tangent line, becomes negative again until I come all the way back down to here, and then I get another minimum, and I can start going up again, and it's positive. So the derivative can tell us something about the shape of the graph, the direction, the characteristic of the function, where it's increasing and where it's decreasing. So if the first derivative is positive, the slope is, I'm sorry, I said that wrong. If the first derivative is positive, the function is increasing, and if the first derivative is negative, the function is decreasing. What happens at these very special points down here between increasing and decreasing? Can't seem to get it to stay there. Okay, so if I know that I have negative slopes and I have positive slopes, and I'm on a continuum between positive and negative, what is right there between positive and negative? 0 is there, which means that the slope of the tangent is 0. So I have some control now over finding derivatives, especially derivatives. If I find derivatives that are at some kind of a peak here, we call these extrema. There we go. Extrema, the slope is 0. Now, again, it doesn't look like it's 0 there, but it truly is. If I take 10 to the negative 6 power is close enough. Okay, let's go to our notes then. Increasing and decreasing functions. Again, when we talk about increasing and decreasing functions, which part of the function are we talking about? Inputs or outputs? Output values. Okay. So the increasing and decreasing output values of a function is what we really should be saying. Here are some tests for increasing and decreasing functions. Let f be a function that is continuous on a closed interval. Okay, and continuous, no gaps. You can draw it from left to right on a closed interval, interval from A to B, and differentiable on the open interval from A to B. So the function is continuous, and the derivative is defined for all of those. Similar to what we have here. This function is continuous, and it is the derivative is defined. We don't get to any point here where it says that the derivative is undefined. So the derivative is defined everywhere. Okay, and now we're talking about an interval. So definitely, if I decided on an interval, we could do that. If the first derivative is greater than or equal to 0, what's another word for greater than or equal to 0? If something's greater than or equal to 0, how about positive? If the first derivative is positive for all the inputs in the interval from A to B, then the function is increasing. In other words, the output values of the function increasing on that interval. So if the first derivative is positive, function is increasing. Tangent lines are going uphill. If the first derivative is negative, then you know that the function is decreasing. So we would have tangent lines that go downhill because the slopes of them are negative. Up here we'd have tangent lines that go uphill because the slopes are positive. And if the first derivative is 0, then the function is constant on that interval. So if for all of those inputs in that interval the derivative is 0, now that's not going to happen that much that we have a horizontal portion of our graph. But what we're saying is that if the first derivative is 0, it's neither, and maybe we should put that in, neither increasing or decreasing. Okay. So the first derivative is going to be now our way of determining a lot about these graphs. Again, chapter 3 is a lot of visual, it's a lot of graphing information. I'm looking forward to actually the last section in this chapter because it talks about optimization and we get into more of the applications that is relevant to what you're about, and that's the business field. Okay, well let's look at the next problem. It says use the